Welcome to our webinar about the next generation transparent conductive coating HeiQ ECOS. My name is HeiQ Romero. I am Digital Marketing Manager at HeiQ, and I will be guiding you for the webinar today. We will have 40 minutes of presentations followed by 20 minutes of Q&A. You can ask questions throughout the presentations by using the Q&A button. Now, let me introduce our speakers today. First up, we have Dr. Oliver Zech. Oliver is CEO of HeiQ RAS in Germany. He studied chemistry in Germany and France and holds a PhD in chemistry and an MBA in general management. His specific focus is on application developments with HeiQ ECOS. Next up, we have Dr. Jochen Manara. Jochen holds a PhD in physics. He is head of the Advanced Thermal Management Group at CAE, the Center for Applied Energy Research. Jochen's focus is on thermal and infrared optical measurement techniques and functional coatings. Then next up, we have Dr. Andreas Distler. Andreas has a PhD in chemistry. Since 2010, he's been working in the field of OPV, organic photovoltaics, up to 2015 in the industry, 2017 in the industry, and since then in academic research. He focuses on upscaling organic photovoltaics. Then our fourth speaker is Dr. Michael Niggemann. Michael studied applied physics. He has a PhD from the Fraunhofer Institute of Solar Energy Systems in Freiburg, Germany. For 6 years, he was CTO at a startup in Cambridge, UK. In 2015, Michael founded his own company, Enerthing. Now I hand over to Oliver to start the presentations.
I hope everyone can see my screen now. Also from my side, welcome to the webinar. I'm very pleased to introduce HeiQ ECOS technology today. And I'm also very much looking forward to the other speakers that will present selected application examples. Before we jump into HeiQ ECOS, let me briefly introduce the HeiQ group. At HeiQ, we stand for differentiate and innovate based on scientific research, specialty materials manufacturing, and we offer the support of consumer ingredient branding. Our driving force is to make everyday products more sustainable whilst delivering superior levels of hygiene, comfort, and protection. HeiQ was born on a HeiQ in 2005 and is listed on the London Stock Exchange since December 2020. HeiQ is a global, diverse, and over 240 people strong company with 7 manufacturing sites, 8 R&D hubs, and more than 30 nationalities. Over 300 brands worldwide are part of our partners. And HeiQ is an innovation powerhouse that uses 7 technology platforms to create innovative products and technologies for the industries where we are active in. And with over 200 innovations, HeiQ is a company that already won numerous awards and that stands for innovation and sustainability. And the HeiQ ECOS technology is one of these technology platforms. HeiQ ECOS is based on silver wires. We manufacture these silver wires via a patented process with very defined size dimensions. So around 30 to 40 nanometers in diameter and 10 to 40 micrometers in length. And we do not make these silver wires in form of a powder, always in form of a dispersion or coating formulation. And this coating formulation can be applied to a variety of substrates. For example, to polymer films, to glass to transparent plastics to textiles and many other substrates. And on the right-hand side here, you can see a SEM image of a coated polymer film. And these tiny white structures that you can see here are the silver wires. And if you take any point on this surface, you can see that we form an interconnected network among the entire surface. And this interconnected network is responsible for conductivity. And the areas that appear gray or black here in the SEM, in the skeleton electron microscope, are transparent to the human eye, at least if you use a transparent substrate. Therefore, with silver wires, with HeiQ ECOS, we can generate transparent and conductive surfaces. And the main parameters that characterize such transparent and conductive surfaces are, on the one hand, the sheet resistance or the conductivity, and on the other hand, the transmission or the transparency. And the blue curve here is our HeiQ ECOS. And what is demonstrated here is that we can cover a huge range of sheet resistances with HeiQ ECOS, simply depending on the amount of silver wires that is deposited on a surface. And this is a very important point because depending on the target application, we need different sheet resistances. And still, from 5 to several hundred ohms per square, we have very good transparency and transmission values. We see 4 main building blocks for target applications. First one is transparent heating. Second one is transparent low E coatings. Third one, signature management and printed electronics. And I will briefly introduce these 4 building blocks, and afterwards we will hear something more detailed concerning selected applications. For transparent heating, on the right-hand side here, you can see the back window of a car. It's a substrate that was coated together with a partner. We made this development with an industry partner that was coated in an industrial process with HeiQ ECOS. Afterwards, bus bars were applied to have a contacting of the layers, and a top coat was applied to protect the silver wires and the layer against influences from outside, and to maintain a good mechanical stability and the stability against water, solvent, against abrasion resistance, and so on. And if you now apply a voltage, we get a very homogeneous surface heating. Even if you apply a low voltage, something between 12 and 24 volts, which is typical values in the automotive arena. And well, this is a quite large substrate here, but of course we can adjust the size of the substrate depending on the target application, and also the heating power can be adjusted depending on the voltage that you apply and depending on the amount of silver wires that you bring on such surfaces. Second example, the low E effect, the low emissivity effect. I would like to show a visualization of this effect, and Jochen Manara will later on show more details what this effect is about and where it can be used. First example here is on the left-hand side, a polymer film coated with HeiQ ECOS. On the right-hand side, the blank, the uncoated substrate. And now we hold our hand in front of this area with a certain distance and look at it with the infrared, with the heat camera. And what we see here is where the HeiQ ECOS is present, the heat that is generated from the hand is reflected back from the surface. Whereas on the right-hand side, the uncoated substrate, it appears blue, so no heat is reflected. And the same effect is shown in this short video. In this video, we printed the HeiQ RAS logo on a transparent substrate, and I'm holding my hand quite close to the surface, look at it with the heat camera, and you can see that the printed logo the heat that is generated from the hand, the printed logo reflects it, and this can be detected in the heat camera. It's a visualization of the low E effect. Transparent printed electronics. Well, as I mentioned, the HeiQ ECOS formulation can be deposited on a variety of substrate, and is also appropriate for roll-to-roll processing, for example, on polymer films. And one target application of this roll-to-roll coating is in the organic photovoltaics, as electrode in organic photovoltaics. And Andreas Distler and Niggemann will later on show where this is used more detailed. One important point is the resource efficiency. For example, for a target conductivity of 100 ohms per square with 10 gram silver wires, you can coat more than 200 square meters of polymer film. So it's a very resource efficient material. And it's also flexible. So if you bend, for example, the polymer film and relax it, you will not lose conductivity. The conductivity remains because the silver wires are very tiny and ductile structures. Well, and finally, signature management. Well, if we can reflect heat radiation, or if we can adjust the degree of heat reflection, we can also adjust the shielding degree of shielding for other wavelength. For example, for EMI shielding, the silver wires can be used. It simply depends on the amount of silver wires that is deposited on a surface, and if you want on the mesh size that you generate with the silver wires. And also in the microwave and radar range, it is appropriate to shield these electromagnetic waves. And the degree of shielding can be adjusted depending on the customer needs and also depending on the target applications. And with that, I would like to hand over to Jochen Manara to present more details concerning low E coatings and silver wires.
Yep, thank you very much for your introduction. Now I will give some short overview of silver nanowires as an application for transparent low E coatings. So you may go to the next slide, please. So I'm from the Center for Applied Energy Research, and we are working on a wide range of activities related to research and development, from the basics to practical applications, for example, the low E coatings. And beside research and development, we are also preparing and characterizing prototypes and demonstrators, as well as we are performing consulting and doing acquisition for funded projects and the management of research networks, as well as providing scientific services and organizing seminars and conferences. And
you're on mute, Jochen.
yeah, no. So now you hear me again, sorry. The research groups are working inter and transdisciplinary. And for example, one working group is the climate neutral buildings and cities, where, for example, low E coatings are applied and play a role for the energy concepts, as well as demonstration and monitoring. We are also active on smart functional materials. That means the preparation of nanostructured materials by a Sol-Gel synthesizes. And in the advanced thermal management, we are working on low E coatings, or in general on thermal and radiative transport, as well as on functional coatings. And finally, the sensors for energy and hydrogen technology. We are performing optical measurements as well as high precision inline processes. But now I want to come to the topic of this presentation, the low E coatings. provided by the silver nanowires. So in general, low E stands for low thermal emissivity, as already mentioned by Oliver Zech. And here you see a visualization of this effect. So on the left, you see a surface with a low E coating, and this low E coating reduces the amount of thermal radiation which is emitted by the surface. In contrast to that, on the right, you see a conventional surface with a high emissivity, which emits a larger amount of thermal radiation. Additionally, the low emissivity equals a high thermal reflectivity R, which has been demonstrated by Oliver Zech already in the video, and which can be shown here or can be seen here on the infrared thermogram. So here on the right, you see a glass sheet without low E coating, and on the left, you see the glass sheet with low E coating, and the heat from the body or from the hand in this case is reflected by the low E coating, whereas the reflection without low E coating is significantly lower. That means the silver nanowires reflect thermal radiations and therefore emit a low amount of thermal radiation into the surrounding. In both cases, the thermal insulation is increased by the low E coating, and you can perform some calculations on this topic. For example, here for glazing, by adding low E coatings to glazings, you can reduce the energy consumption by increasing the thermal insulation. And this can lead to a saving of heating as well as of cooling energy. So single glassing, that means a single glass sheet provides a very poor U value. U value is the heat transfer coefficient. And here you have an U value around 6 watts per square meter in Kelvin. This can be halved by adding a second glass sheet. Then you have a double glazing. And by adding, next, please? By adding a low E coating on the glass sheet, you can reduce or halve the U value again. And finally, you can get to the triple glazing. So the next slide, please. And for the triple glazing, you have 2 low E coatings. And again, you can halve the U value by these low E coatings and by the additional glass sheet. That means by providing transparent low E coatings in this case, the heat transfer can be significantly reduced, and therefore the thermal insulation can be significantly increased. Of course, the exact value not only depends on the emissivity, but also on the filling gas, like argon or air, for example. And the same can be done for wall constructions, especially for external walls. So next slide, please. Here you see a typical heat transfer coefficient of buildings due to the age of the construction of the building. So old buildings have high U values usually. For example, before 1977, you have U values of about 2 watts per square meter in Kelvin, whereas for very new buildings, you have significantly lower U values. In general, you have a high emissivity for typical wall constructions. So on the right, you see just a picture of an external wall, and then by adding a low E coating, which is shown here in blue, the emissivity of the surface can be reduced, and this reduces the U value of the construction of the wall. So in the table, you see the U value given for emissivity of 0.1 instead of 0.9. And so on the next table, you see the reduction in percent. That means for all buildings, the U value can reduce by 20 to 30%, whereas for new buildings, the U value can reduce by about 5% when applying a low E coating. And in this case, a transparent low E coating has the advantage that you can see the color of the wall through the transparent low E coating, which provides the low emissivity. So on the next slide, you see the increase of the thermal comfort. So beside increasing the thermal insulation of the wall construction, you also increase the thermal comfort inside the room, because a person inside the room emits thermal radiation into the surrounding. Of course, the surrounding also emits thermal radiation to the person, like from the internal wall, but also from the external wall. And during winter times, the temperature of the external wall may be very low or relatively low, depending on the U value of the external wall. And by applying a low E coating on the inner side of the external wall, part of the thermal radiation from the room or from the person in the room is reflected by the external wall, and therefore the person feels more comfortable inside the room, and then you have an increased thermal comfort and an increased perceived temperature inside the room. The same is valid for summer times. Here, for example, so next please, you see an interior sunscreen behind the glazing, and during summertime the sun or the solar radiation goes through the window or the glazing and heats up the internal sunscreen, and then the sunscreen emits thermal radiation into the room, and during summer times this reduces the thermal comfort. But by applying a low E coating on the internal sunscreen, you can reduce the thermal radiation emitted into the room and therefore increase the thermal comfort also in summer times. So on the next slide, you see the values for typical low E coatings based on silver nanowires. So as already mentioned, we want to have a high transmissivity in the visible spectral region and a low emissivity in the infrared spectral region. And low emissivity in the infrared spectral region means high reflectivity in the infrared spectral region. So here you see the graph. The transmissivity in green and the reflectivity in red is printed over the wavelengths. And next, you see the wavelengths range from the visible or from the ultraviolet spectral region over the visible towards the infrared region. And in this case, you see a typical silver wire nano coating with a high transmissivity of about 72%. Next, and low infrared emissivity of about 21%, which equals a high reflectivity in the infrared. So next, please. Here you see again an SEM picture or scanning electron microscope picture of the silver nanowire coating. And as already mentioned by Oliver Zech, the connection between the silver nanowire provide high electrical conductivity and additionally reflectance or reflectivity of the infrared radiation. That means wavelengths above 5 microns are reflected by this structure, whereas wavelengths below 1 micron or below 800 nanometers, that means the visible spectral region, can transmit or is transmitted through this structure, as the distances between the wires are larger than 1 micron and therefore provide a high transmissivity in the visible spectral region. So I come to the conclusions of this presentation. So in general, the fields of applications are, as already mentioned, in the building sector, the walls, but also the glazings or greenhouses, as already mentioned. Especially membrane constructions are of interest. Here you see the ice arena in Landsberg am Lech, which is or where a low E coating is applied on a suspended ceiling in order to improve the thermal properties of the building. The same can be done for transparent constructions like, for example, for the Royal Palace in Dresden. So the courtyard is covered by a transparent conduction, up to now without low E coating, but by applying low E coatings, the thermal comfort can be increased. And beside buildings, of course, technical applications are of interest for example, automotive or aerospace applications where thermal comfort or thermal insulation is of increasing importance. Also industrial processes, and further developments would be the adjustment of the properties like the combination of emissivity and transmissivity, or the adjustment of the haze, usually low haze, but for some applications also larger haze would be desirable. And finally, the adaptation on the substrates would be of interest, like applying the coating on different polymeric materials, on textile fabrics with a high adhesion and high stability. So thank you very much for your attention. So the next slide, please. Yeah.
So welcome from my side as well. My name is Andreas Distler. I'm group leader of organic photovoltaics at the Friedrich-Alexander University in Erlangen-Nuremberg. And the research focus of my group is the upscaling of such photovoltaic technology. So everybody knows what photovoltaics are, solar modules, we all know them. Most of you also know what organic materials are, like carbon-based chemistry materials, and everybody knows printing. But all of these three things together, what is this? What is printing organic photovoltaics, and why would we want to print solar modules? So we all know these conventional photovoltaics on the rooftop, for example, most of them silicon-based. They are a very important source for renewable energy. And but to be honest, they look a little bit boring, and they are heavy, they are opaque, and not flexible. So what if photovoltaics could also look like this? And actually they can by making organic photovoltaics. So you see here already lots of benefits, like, for example, the design. They can be transparent, you can tune the color, and you have a freedom of shape, so you can basically pattern them in any shape you want. They are very thin, lightweight, and flexible, so you can integrate them into lightweight architectural structures or wearables, for example. They have some technology advantages, which I won't go into detail, but for example, they have a positive temperature dependency, which means that in contrast to silicon modules, which actually get a lower performance if they heat up during the summer at noontime, they actually remain their efficiency or even get a little bit better when they get hot. And a very important benefit is that you can manufacture them in a roll-to-roll printing process, which means with a high throughput and at low cost and energy expenditure. So the organic materials, which are the active layer in this material, in this solar cell stack, they provide all these characteristics. But if we want to make a solar cell stack, also the electrode materials need to provide these characteristics. For example, they need to be transparent, otherwise we can't look through the module. So let's take a look at the architecture of such solar modules, take a look inside. The layers that are printed onto a substrate, and the substrate is actually already 99% of the thickness of the whole module. Because the whole layer stack that is printed on top is actually less than 1 micrometer thick. So in the center, we have an active layer, the active material, which is organic. That's why it's called organic solar cell, which is usually a polymer or a small molecule, so carbon-based materials. And this absorbs the light, the photons, and converts them into positive and negative charges, which are then directed by an hole transport layer and an electron transport layer on the top and below this layer. So the one lets only positive charges pass and the other one only negative charges pass, so that we can extract the current out of the solar module. And now, most importantly for this talk, are the electrodes. On the one hand, we have a top electrode, which is also called back electrode, because the light comes here from the bottom through the substrate into the solar cell, and this electrode is on the back side, which is usually a thermally evaporated silver or a screen printed silver paste electrode. And the drawback is, of course, that those materials are opaque, so you can't look through the module. Then on the other side, the front electrode or bottom electrode is usually a TCO, a transparent conductive oxide, like ITO, indium tin oxide. And this material obviously needs to be transparent because that's where the light comes from into the solar cell. So this needs to be highly transmissive. The drawback for the standard materials is that they are sputtered and because of this, not solution processable, printable. So if we want to replace those materials, those electrodes with the silver nanowires from HeiQ ECOS ink, if we want to replace the top electrode in order to obtain semi-transparent solar modules, we need low sheet resistance values below 20 ohms per square and fairly high transparency because we want to look through the module. Also, the haze should be quite low because it should not only be translucent, but also we want to really have a clear vision through the module. So less light scattering as possible. And obviously we need homogeneous coatings because the modules have to have a nice appearance. And for roll-to-roll printing, especially with the organic active materials underneath, we need a low temperature processing condition because the materials are sensitive to high temperatures. So we need to stay below 120 degrees. If we want to replace the bottom electrode with silver nanowires, the requirements are similar. We also need a low sheet resistance, but this time we need a very high transparency because that is actually, this layer is in between the sun and the actual solar cell. So everything that absorbs or reflects at this position will decrease the current of the module. And another very important requirement for bottom electrodes is we need a very smooth surface without agglomerates because, as I said, the whole solar cell stack is less than 1 micrometer thick. And if the agglomerates of silver nanowires, for example, are larger than that, this would shunt or even short the device completely. And again, we need homogeneous prints. So we had 2 projects together with HeiQ RAS to develop organic photovoltaics with their ECOS nanowire inks. The one is called low haze. There we developed the roll-to-roll printing process for this for the silver nanowire coatings with a very low haze value, so less than 5% diffuse light. And this was achieved by HeiQ RAS by making the silver nanowires thinner down to 30 nanometers in diameter, which is the main driving factor for creating a hazy appearance. These coatings were fairly mechanically stable, so we were able to rewind and unwind and rewind several times this roll without causing any changes in the sheet resistance, which is an important factor for manufacturing on a large scale. The sheet resistance transmission ratio was very good. The only drawback, so we reached more than 80% transmission at less than 20 ohms per square sheet resistance as desired. The only drawback was that we needed to anneal it at 150 degrees to reach these values at that point. Yeah, so this could have been better. But we tried it in our solar modules as top electrode and it worked perfectly fine. So you can see one of these semi-transparent modules with ECOS top electrode. The second project, which is actually still ongoing, is OPV for IoT. And in this one, HeiQ RAS developed their ink even further. And this time we really achieve homogeneous coatings and great sheet resistances and great transmission values without even having to anneal the layers at 150 degrees. Not at all, or even at 120, we reached the maximum trade-off already. So that was a huge improvement and a very good achievement in this project. And the second very good achievement in this project was achieved by HeiQ RAS by special purification of the ink so that we don't have any agglomerates in that layer, which is the prerequisite for using it as a bottom electrode. And that's what we did then. So we replaced a sputtered bottom electrode with the ECOS nanowires in our solar cells, and the performance was comparable. And last but not least, we also made modules out of this layer stack with ECOS nanowires top and bottom electrode, which is actually not too easy because for creating a module, you need to connect several solar cells in series. And the so-called interconnects are the regions where the top and the bottom electrodes come in contact and have to conduct all the current. And if both electrodes are silver nanowires, this contact area is really, really very, very low. And but we achieved to make modules and connect several cells in series with good performance and achieve a good interconnecting between silver nanowire top and bottom electrode. And to conclude my talk, I would just like to show some pictures for potential applications of this technology, organic photovoltaics. Where does the journey go? For example, huge application markets are consumer electronics, chargers for portable devices, wearables, indoor shading elements, outdoor building integration. Greenhouses, for example, is a huge market, huge architectural structures, and even space applications are an important market because of the very, very low weight of these modules. And with this, I'd like to close my talk and I stay available for questions afterwards. Thank you.
Okay, I'd like to continue my presentation. So I will kind of continue where Andreas Distler stopped. So we are working on the application side. So my name is Niggemann from Enerthing, and I will talk about accelerated decarbonization of buildings by sensor retrofit digitalization. So I go to the next slide. Yes. So what we see is from our company Enerthing's perspective that buildings are under high pressure. So we've talked about buildings in the previous presentations, but that related more into the energetic properties of buildings, and we have a different view on buildings from a different perspective. So what we see is now, since the topic of new work, that buildings are not used anymore in the way they were used in the past. So this is something that has changed recently. Then another topic is CO2 emissions of buildings have to be reduced significantly within the next 30 years. And also we know spending time in buildings, we know air quality is very important. So if you go to the next slide, so what we see regarding the energy consumption of buildings, that 30% of the CO2 emission arises from buildings, and primarily from building operation. And what happened in the previous years, so starting from the climate agreement in Paris, the new EU taxonomy, and also the increasing CO2 tax, there's an increasing pressure on buildings to change with respect to their CO2 emissions during operation. And the ambitious target is in 2045 to get to zero CO2 emission, so a net climate neutrality, and this is a really important goal. If you go to the next slide, please. So what we see, by digitization of these buildings, first of all, you can reduce CO2 emissions, so increase energy efficiency. Then you can also improve the work space management. So that relates to buildings that are not fully occupied all the time. And you can care about the air quality and health within buildings. And if you go to the next slide, if you now look at the building stock, you see that 80% of the buildings don't provide this data to do the optimization. So there's no data to improve the room climate. So there's no data on the room level for monitoring and controlling the room conditions. There's no data about the occupancy of workspaces, of office buildings, and there's very little data on air quality within these buildings. If you go to the next slide, please. So, so how to, let's say, digitize those buildings? There are only two ways nowadays. So the first way is you start retrofitting buildings with wired sensors. And that's effectively a very expensive approach. It takes time, and nowadays, even though there's no workforce to do this work, so this is a way that won't happen in the significantly large building stock. So if you look, then the other option is you start with wireless sensors. And then you cut off the wiring out of the equation, but you still are stuck with the powering of those devices, and that results in effectively in additional maintenance work that's needed, replacing batteries after a year or a couple of years, and this is not a very sustainable approach, and it's very expensive because you have to pay for the workforce to do the maintenance of your device. So the solution is, if you go please to the next slide, is so what we've developed, and that now a long story that relates to the technology Andreas has mentioned, the organic photovoltaics technology. So this is a technology that not only works under sunlight, but also is very, very efficient under artificial light, so indoor conditions. So what this does is effectively it generates sufficient power to replace primary batteries. And this is what we've developed at Enerthing. So we've developed a way to gather data from on the room level by powering wireless devices with artificial light. So in principle, your pocket calculator, but in a very advanced form. And on this platform, we've implemented several types of sensors. We can measure occupancy, we can measure room climate, temperature, humidity, but also the CO2 concentration in air. And by combining this with a wireless technology called LoRaWAN with a long-range communication technology, we can retrofit buildings very fast. So within a couple of days, your building is transformed from the old 80s building to a modern building, providing the important data. So it's very fast and it's also sustainable. If you go to the next slide, please. So this is what you can see here. So by gathering this data, effectively, you make your building transparent with respect to the utilization, with respect to the needs for temperature and humidity, and also with respect to the air quality. And by combining this with building automation, so you utilize this data to control the temperature on the room level, but you can also make use of the data for the building management system. And this way you can save energy up to 30%. You can reduce the office space or change the utilization to office space, and you increase the health in your company. If you go one slide further, please. So so we've done calculations, and that also really affects large real estate companies. So how to improve the energy efficiency on the path towards net zero. And by retrofitting these with sensors and improving the energy efficiency by 20%, you can significantly reduce the cost within a day. Effectively, you reduce your energy costs by more than by 18,000 euros per year for such a building. So this is 20% cost reduction, and you end up with a return on invest of less than 12 months, but only by digitizing the buildings and improving the energy efficiency. If you go to the next slide, please. So what we've done here, so what is part of Enerthing is the technology knowledge. So this is the way how we differentiate in our product. So we have an internal roll-to-roll production. As Andreas also already described, so this is a coating process, and based on this, we produce these indoor modules. And as part of the project OPV for IoT, Andreas has mentioned, we explore these transparent electrodes to further improve the organic photovoltaic material, because at the end, energy efficiency is the key to produce the data we need for optimizing buildings. So there's a long path, but it's very important to optimize. So every photon we convert into a data point improves the efficiency of buildings at the end. And this is where nanowires play a role to make the organic photovoltaics under low light conditions even more efficient and also reduce the production cost. If you go to the next slide, please. So you have a short glimpse in our facilities here in Leverkusen. So it's an in-house roll-to-roll production, and with the 10 times 10 centimeter square modules, we have a capacity of approximately 25,000 of those modules per month. And we can also change and vary the lengths from 10 to 100 centimeters. And yeah, very open to discuss also about our production. And if you go to the next slide, I think this should be the end. So yeah, I'm looking forward to the discussions, and thank you very much for attending this webinar.
Thank you very much to all our speakers. That's very in-depth, and I'm sure we'll have very well corresponding in-depth questions coming up. So yeah, all speakers, please, yeah, turn off your mics and let's get started. We already have a few questions that were asked, but to anybody who has questions and hasn't asked them yet, please use the Q&A function. Just click on the button and ask your question. If in case we don't get to your question, we will answer them later by email. So as long as you don't use the anonymous function, then we cannot do anything about it. But you ask your questions, we will get to you now or later by email. Right, let's start up with the first questions. They came in pretty early. So it's actually a question for understanding. Our asker doesn't understand the working principle. Does silver absorb energy or does it reflect it? For example, ITO absorbs. Who wants to answer this question? Maybe Oliver?
I could, but I think Jochen Manara is the expert in this field.
Okay.
So
yeah.
Over to him.
Yes. Yeah. The silver nanowires reflect the thermal radiation. That means you have a high reflection of thermal radiation provided by the coating of the silver nanowires. And this means at the same time you have a low emission of thermal radiation. That means a low E property of the silver nanowire. Is that okay for the answer?
I should think so, yes. Then let's go on. Does it only work in a clear coat?
Yes, of course. The properties of the silver nanowire coating not only depends on the silver nanowires itself, but also on the matrix material of the coating. So you have to choose an optimal combination of the silver nanowires and the material to coat the silver nanowires. Maybe Oliver can also talk something about this.
Yeah, sure. I think that's exactly the point where we from HeiQ side can also support our partners and customers. As was mentioned, I think during the talk, our silver wires are appropriate to be dispersed in aqueous systems, but also in, for example, alcohol solvent-based systems. And well, depending, let's say, on the formulation that the customer wants to use, we can optimize the ratio of, let's say, silver to binder, and get the best properties and performance.
Okay, thank you very much. Next question. Which coating chemistries are compatible with silver nanowires and which are not?
Well, I think as I mentioned, with aqueous systems, we know that it works very well. With alcohol-based systems, we also know that it normally works. But of course, for each binder, let's say we have to first check the compatibility. If the silver wires can be mixed into this special coating formulation, because often customers have custom designed formulations, very special ingredients, but it goes quite quickly to check if the silver wires are compatible with these coatings. And as I already mentioned, principal conventional coating techniques can be used. So it can be roll-to-roll processed, slot die coated, screen printed, spray coated. So there are many techniques that can be used for conventional coatings and they're state of the art.
Okay, thank you very much. Next question, very technical. How much cost could be saved if these electrodes were used instead of the conventional ones, e.g. ITO? Who wants to answer this question?
Well, I could say some words about that. As I mentioned, the silver wires are very resource efficient. And I think one other advantage is that they can be liquid processed, so they don't need expensive sputtering processes. But to have a detailed calculation of costs, we would need to know more about the target application, because as I mentioned, depending on the target application, we need a different surface conductivity. Surface conductivity, again, is adjusted by the amount of silver on the surface, and the amount of silver affects the price finally. But compared to ITO, we can achieve significantly lower prices if you compare to state-of-the-art ITO that is available on the market. And if you would like to have more details about that, we can probably make a bilateral discussion, provide more details.
Okay, so the next question is how much do these inks cost? Is also depends on application.
Yeah, but we will be happy to share the prices in bilateral talks. And if you know more about your special request, we can also send a specified quotation about that.
Mm-hmm. Okay, and next question. You talked about applications on the wall, but do you normally apply comprehensive and colored products on the walls? I guess this means mixed in with paints.
Yes, that's correct. So usually you would apply a paint on the wall or a colored paint, depending what you like to have on the wall. But it's not so easy to apply a colored painting with low E properties on the wall. Therefore, an additional coating with a transparent material which provides the low E properties would be an idea to improve the thermal comfort. The question is how to apply this transparent low E coating on the wall, maybe with foils or membrane constructions or something like this. This would be future work to really get the combination of color impression of the wall in combination with the low E properties of the surface of the wall. And one possibility would be a transparent low E coating on the colored wall.
Okay, thank you very much. So that means if you are interested in paint and walls, get in contact with Oliver to set up a project and find out what can be done. Okay, thank you. Next question. Does the AGNM need an overcoating for protection against O2, water, or is there some kind of protection agent inside the mixture?
Mm-hmm. Well, we do already have some protection agents inside the coating formulations, also wetting additives, for example, to improve the wetting behavior on surfaces. But again, this depends then on the target application. If you need a high mechanical stability and abrasion resistance, then we would recommend to use a top coat to protect the silver wires.
Okay, thank you very much. Next question is, how are new end products applications created? Do you have exclusive partnerships? Oliver?
Well,
Yes.
yeah. Well, we are still in a quite early stage with this ECOS technology, and we are actively searching for partners. For some applications, we are already working together with partners to reach the target applications. If we have any exclusive agreements, this is something that we would publish separately.
Okay, thank you very much. Next question. Have you studied some applications in the textile industry to give electrical conductivity to the fabrics?
well, as HeiQ is a company that is very much involved in textiles and textile coatings, we of course also did already tests concerning the coating of textiles. And at least in a lab scale, we see that we can make very nice conductive surfaces on textiles, since the silver wires are very ductile and they really wrap around these textile fibers. So we would also have more details about that. If you're interested, please contact me. I'll provide that information.
Thank you. Next questions. What kind of coating can be used in medical systems today, especially layer by layer or electrode systems that you mentioned at the beginning?
In medical systems, well, in principle, if you want to protect the silver wires, you can use top coats that are conventionally used also for medical devices and medical systems. I don't know if I got the question right.
Yeah, especially layer by layer or electrode systems.
Layer by layer, yes, sure. I mean, you can first deposit a base coat with silver wires, and afterwards you can apply several other layers, for example, top coats, or in the example of the organic photovoltaics, you have seen that we have had many different layers, different active layers that are necessary, but this is in principle possible, yes.
Next, do the inks contain some conductive additive, and if yes, which one?
Again, please.
Does it contain some conductive additive, and if yes, which one?
The conductive additive are the silver wires only, and this is this is what our formulation is made of and based off.
Okay, so the main ingredient is the conductive additive. Okay. Next question, is the product suitable for textile coating in a water-based compound? Can it reach conductivity under 10 -6 ohm?
So this is the antistatic region. So we can also reach let's say lower conductivities if we deposit less of silver wires on surfaces, for example, on textiles. But again, for each application, we have to check what requirements are necessary. We have to check, do we need additional material? Do we need, for example, a top coat? Don't we need that? So I'm happy to discuss this more detailed separately.
Okay, next question. If coated on battle dress uniforms, should this be at the inside or the outside? Is this washable at 60 degrees Celsius? And during day in, day out, normally they use 2 years in their BTU. Will this coating withstand this period? What is the actual TRL level for this specific application? A lot of questions. So for battle dress uniforms, what would you say?
Good. I think first, where the coating is applied, I think there are really in the military arena or defense arena experts if it should be applied directly at the outer surface, at the inner surface. I think it depends also a little bit where and for what it should be used. And concerning washing stability, if you apply a conventional top coat, of course, the washing stability is then given. If we want to have the wires directly at the surface, then we have to combine the wires with a binder. And therefore, well, often customers already have their preferred binder system. So I think it would be a good way to directly check if the silver wires are compatible with the binder, make the right dilution and the correct ratio, and then we can check, depending on this target application, also the washing stability.
Okay. Maybe a question for Andreas. Are the solar panels you described already on the market?
Some of them are. So, for example, this huge architectural arena I've shown, that is the Novartis pavilion, for example. So there are some companies which do this. I mean, Enerthing is also a company which brings these modules to the market. But I wouldn't say that they entered the market to an extent as as it is prospected that it will in the future. So at the moment, it's still some small niche where the products are. But yes, there are some companies and which provide these modules on the market, but rather in the B2B business and not to the customers directly.
Okay, so this is you guys are front runners when it comes to this. Yes. I see. Okay. Okay, thank you very much. I see we've reached the end of our webinar time. So any questions that weren't answered during this webinar, we will get back to you by email. Do not worry.
But just briefly
also,
to add, we are on the market with our modules, so please get in touch if you have any questions. So I'm happy to answer these questions in detail. Yeah, okay, we are manufacturing, so yeah.
Okay, so if they're on the market, get in touch with Michael. Okay, right, and just to say that end of this month, HeiQ will be exhibiting at the European Coating Show. So if you want to meet us in person, you can also do that in Nuremberg, Germany, at the European Coating Show. The recording of this webinar will be sent to everybody who signed up, so you can rewatch it later. And also, if you think of other questions, do not hesitate to write. If it's for one of the speakers, I will forward and, just get the conversation going. Thank you very much. We hold webinars frequently at HeiQ about material innovation topics. Keep an eye out. Okay, thank you very much. Thank you, speakers, for coming, and see you next time. Okay, thanks. Bye-bye.
Bye, thank you.